Now that we've tackled the idea of equilibrium and talked about the equilibrium constant and how to calculate it and how to deal with the equilibrium that happens in a heterogeneous situation, i.e. with solids or liquids at combination of either solids and liquids, gases, aqueous, whatever it may be. Now it's time to look at the calculations that we can do with the equilibrium constant. So this is 15.5 and 15.6 in your textbook. From the basic standpoint, we can just look at plugging in equilibrium values to get the equilibrium constant. So we would take the expression for the equilibrium constant, and so what do we have here? So at equilibrium, the concentrations are given to at equilibrium. Now in the lab, it's oftentimes much harder to get the to get those values than it is from just a problem giving you the values. So if we do a calculation, I believe we get 8, 4 divided by 0.5, so 8 would be equilibrium constant here. And for the equilibrium constant, we do not include units. So it's a dimensionless value. All right, now here's a situation where we're combining hydrogen and iodine in a 2-liter container initially, and then at equilibrium we're told that the concentration of the hydrogen iodide that's produced is 1 molar, and it wants to know the value of the equilibrium constant here. Now from here on out, we're going to use this table to actually create, oops, that's not what I wanted to do. We're going to use this table to help organize our work. First of all, we're given that we have 4.00 moles of the H2, and that's in 2.0 liters. We have 6.0 moles of the I2, and that's in 2.0 liters. And these are both initial concentrations. And then we also know that, we don't know we're assuming that the initial amount of this is the hydrogen iodide is 0. And that we're going to go to an equilibrium concentration of 1.0 molar. Now we can kind of use a little bit of logic here and realize that, well, if the HI is 1.0 molar and we've got 2 liters of, our container is 2 liters, that means that we have actually formed 2 moles of the hydrogen iodide. So we can do the stoichiometry and figure out how much of the I2 had reacted. So if we formed 2 moles of HI, we must have reacted 1 mole of I2, which would then decrease that number of moles to 5 moles, and the H2 would have decreased from 4 moles to 3 moles in the 2 liters. However, what happens is when we do these equilibrium problems, the solution volume, or the volume of the container of gases, is always going to stay the same, or at least in most cases. So we're actually going to fill values into this table that correspond to the concentrations. And we're going to put in the initial, the change, and the equilibrium. Right? So we're going to organize our work this way in this kind of a table. So I should see a lot of these tables in your homework and from all the problems that we do in class. So our initial concentrations for the hydrogen, doing the calculation there, we would have 2 molar for the hydrogen to start with. We would have 3 molar for the concentration of the I2, 0 molar for the HI, and of course we're told that the HI concentration at equilibrium is 1.0 molar, which means that it went up by 1.0 molar. If the HI goes up by 1.0 molar, we're looking at the stoichiometry of the reaction. If that goes up by 2, the iodine and the hydrogen both will have gone down by half that amount, given the stoichiometry. So down by 0.5 molar, down by 0.5 molar. So at equilibrium, we would have 1.5 molar H2 and 2.5 molar in the I2. Now we're ready to go ahead and use our equilibrium expression. The HI concentration at equilibrium squared divided by the H2 concentration at equilibrium and the I2 concentration at equilibrium. And again, it's imperative that you remember that these concentrations have to be the equilibrium concentrations. You're always going to plug these values into that formula. Don't go plugging in other values into there or you'll get it wrong. So we'd have 1.0 squared divided by 1.5 times 2.5, and these are all molarities, which gives us 0.267 for the KC. And I'm guessing you probably can't have quite that many significant figures, so we probably have to eliminate that one there. So it would be 0.27 for the KC value. All right, in this one's a very similar problem. Again, we have our initial, our change, and our equilibrium values. We're given the molarities right off the bat. So this is 2.00 molar. The O2 is 1.50 molar. The SO3 initial is 3.00 molar. And we're told that the sulfur trioxide at equilibrium is 3.50 molar. So we know that the equilibrium, even though we have everything there, we know that the equilibrium must have gone to the right. The equilibrium went to the right to get to equilibrium because the SO3 concentration went up. So that went up by 0.50 molar. So the other two, the reactants, must have gone down. Since there's a 2-to-2 ratio for the SO2 and the SO3, the SO2 would have gone down by 0.50. And the oxygen, since there's a 1-to-2 ratio, it only changes by half as much. So this would have gone down by 0.25. And then we can fill in our values. Oops. So at equilibrium, we would have 1.50 for the concentration of sulfur dioxide, 1.25 for the concentration of the H2O, and then 3.50 for the concentration of the SO2. So if you do the calculation for this, which I'm going to fill it in now because we have some other things to work on, but it's going to give you 4.36 as the equilibrium constant. Probably be a good idea for you to practice if you're not sure about your math and plugging in to go ahead and try that and confirm that that's the answer that you did get. This is an interesting one that involves pressure. So you've got a solid that's in equilibrium with two gases. And so obviously that solid's decomposing into the gases. And you're given the volume of the container and the temperature. And you find out that the total pressure at the end ends up being 0.200 atmospheres, and you've got some of the solid left over, which is important because if there's no solid left over, then you don't have an equilibrium. You have to have that solid to show that you actually have substances on both sides of the equilibrium. Now what's interesting here is that because the total pressure is 0.2 atmospheres, your two gases are the only thing that's causing that pressure, and they're in a 1-to-1 ratio, which means that if your pressure total is equal to 0.200 atmospheres, that's equal to the pressure of the ammonia plus the pressure of the hydrogen sulfide. Right? And those two pressures have to be the same, which tells you that each of those pressures, the pressure of the NH3 has to equal the pressure of the H2S, which has to equal 0.100 atmospheres. All right, so using that partial pressure idea, you can then use that to figure out the value for the Kp, which would be equal to the pressure of the NH3 times the pressure of the H2S, the partial pressures of these. So obviously if you plug those values in, your Kp is going to be equal to 0.01 0, so that would be our Kp value. And remember that Kp is equal to Kc times RT raised to the delta N power. And remember the delta N is going to be moles of product gas minus moles of reactant gas. So in this case, delta N is going to be equal to 2. So if you plug this in, you can go ahead and figure out the value for Kc. So if we rearrange our equation, we would have the Kc would be equal to the Kp divided by RT delta N. Kp is 0.0100, R 0.0821 liter atmospheres per k mole, times T 295 K, and then again we're going to raise that all to the delta N, or the second power there. So I believe if you put this in your calculator, you end up with 1.70 times 10 to the negative fifth for the value of Kc. This one. So this one presents an interesting dilemma. So we're going to go ahead and set it up again. So we got initial, change, equilibrium, and we're told that we have 0.5 moles of hydrogen iodide in a 1 liter container. So this would be 0.5 molar for our concentration. And we know the temperature, which is important because the equilibrium constant will change at different temperatures. So you always have to specify the temperature. And we know the equilibrium constant. So we know that Kc is equal to 54.3. And it wants us to calculate the equilibrium concentrations of each. So we're basically to assume that we know that there's none of this present in the container. So how do we know what it's going to change by? Well, this is where we use our algebra. And so we can say, well, we know that the equilibrium is going to go to the left. So the hydrogen and iodide have to go up. So let's make hydrogen go up by x. Iodide, stoichiometrically, will go up by the same amount. So it's going to go up by x as well, which means that the HI will go down by 2x. Equilibrium then, concentration of H2 is x, I2 is x, and HI is 0.5 minus 2x. And then what we're going to do is we're going to plug this into the equilibrium expression. So we have Kc equals the concentration of HI squared at equilibrium. So we're going to have 0.5 minus 2x raised to the second power. And on the bottom we just have the concentration of the hydrogen times the concentration of the iodide. And since we know the value of Kc, the only thing we don't know is x. Now, if we leave it as is, it creates kind of a complicated math situation. Fortunately, we're going to be able to avoid this. All these problems, you should be able to avoid using the quadratic in one way or another. This time what we're going to do is we're going to take the square root of each side. Okay, you'll notice that if we take the square root of each side, and I'm going to go ahead and plug the Kc value in here, I'm going to have the square root of 54.3 is equal to, now if I take the square root of this, I'm going to get 0.5 minus 2x for the top, and I've got x times x on the bottom, so that would just be x. Continuing on with the math then, and the square root of 54.3 times x is equal to 0.5 minus 2x. If I bring the x's over on the left and leave the 0.5 over on the right, and then you divide, what I'm going to find is that x is equal to 0.0535. So the change in the concentrations, you can go back up to your table then and plug those values in. So those are going to be the concentrations of the H2 and the I2, and then you would subtract 2 times those to get the concentration of the I at equilibrium. Right? So the trick for this problem was, once we used the algebraic variables to fill in our equilibrium table, and then we were able to take the square root of each side to eliminate kind of the messy math part to this. All right, one final little trick in doing these. This problem we know the value for the Kc. So Kc is 3.80 times 10 to the negative fifth. And again, we're given the temperature of that. And we're starting with 1 mole of I2 in the 2-liter flask. So we've got initial, change, equilibrium. We know that this concentration is going to be 0.5 molar. Again, 1 mole in 2 liters. And we want to calculate the concentration of I2 and I at equilibrium. So we have none of this. And so we can use our unknown variables again. We know that the concentration of the I2 is going to go down by x, and the I concentration would go up by 2x. So that's going to make that 2x, and this one 0.5 minus x. Now when we go to fill this into the equilibrium expression, we'll have Kc, which is 3.8 times 10 to the minus fifth, is equal to the 2x squared divided by 0.5 minus x on the bottom. Now we can't apply the trick that we used in the last one where we take the square root of each side. So we could do this with a quadratic, but we can also do it by making a little assumption. If we look at the value for Kc, we realize that it's pretty small. Right? This trick is going to apply for any Kc that is less than 10 to the minus fourth. Okay? So with that small Kc, what that means is that very little of the H2 is going to be converted over into Hi. So when I look at the denominator here, that minus x, the 0.5 minus x here in the denominator, x should be very small. So I'm going to assume that x is small compared to 0.5. Right. If I do that, my expression then is 2.8 times 10 to the minus fifth is equal to, and I'm going to go ahead and square that number, so I get 4x squared divided by 0.5. So again, if that x is small, I'm just going to eliminate it. And then I can do my math, multiply each side by 0.5 and divide by 4 and take the square root. And if I do that, I get x being equal to 0.00218. And then what I need to do is go back up here and say, yes, the x is less than, and usually the rule of thumb is that x needs to be less than 5% of the number you're subtracting it of. So or subtracting it from, or adding it to. So x is less than 5% of 0.5, or in other words, the error that's created by assuming that x is negligible is less than 5%, and so you're allowed to do that. Nowadays, with today's calculators, you can either, graphically, it's not that hard to do do the quadratic, but again, most of the time you're going to be able to assume that x is negligible or use the square root trick. All right. So now it's just time to do some of these practice problems and get our feet wet with this.